Okay, so welcome. My group and I, we're going to talk about gerrymandering today. So let's just get right into it. So looking at some background and some history, we have Governor Elbridge Gerry here, and in 1892, he was changing some of the Massachusetts regions in the United States, voting regions, so that he could gain some advantage in the polls. And it's kind of funny, actually, because the local newspaper at the time, they got a hold of this information and they published a little cartoon. And they said, oh, this looks really silly, actually. And so here's the cartoon that they published. And to them, it looked a little bit like a salamander, right? So they took what he did with the regions, changing the regions, took his name and took salamander, what it looks like he was doing, put them together, and we get gerrymandering. And so, yeah, that's it. Gerrymandering is when you change regions, political regions, for voting in this case. Okay, and so we're going to actually analyze a little bit at the end of the presentation. We're going to analyze some parts of Massachusetts here. So that was just a very basic background and history of gerrymandering. We are going to get into how gerrymandering can change outcomes of votes. And perhaps it's not obvious how this is a bad thing. So let me show you. So here's my circle city, my imaginary city, and I've placed red and blue centers of people, and the color red or blue represents their preference for voting. So if I cut this city up into 4 pieces, or this region, whatever it is, we cut it up into 4 pieces, we can see there is roughly even preference in the pieces. Some pieces favor one color over others, but it's normally just a little bit if they do at all. And this is kind of a normal way that you would want to cut up a region, right? Just using some straight lines. We'll come back to that in a few minutes. But if I take my city, I can apply some gerrymandering to it here. And maybe I'm on the red team here, right? And I get to cut up these regions. And I'm saying, okay, well, there are more blue regions here than there are red. So we're in trouble. Well, what if we group all the blue together so they're just one region? And so now in this picture, after my gerrymandering, there are 5 regions that favor red and only 2 that favor blue. So here I've highlighted the red and the blue for you here so that you can get a better look at it. But that's how they take voting and people and change the borders so that they can get what they want. Okay? Just to get an unfair advantage. So, okay, let's look now at one of the scores that we can give a region, which shows how compact it is. And it shows how much the region is likely to have been manipulated in some way. So this is the Rioch score, the first one that we're going to look at. And we're going to come back to this a little bit later here. But it's essentially saying that natural regions should be somewhat circular. You might expect that a region would be circular. And then the more that your region deviates from a circle, that means it's the more you're trying to deceive people or misrepresent what you have here. And it's comparing the area of your region with the area of the circle. So let me show you. I have a region here in red, this red rectangle, and it's enclosed in a circle. So the area of my red region, this is a pretty simple area to find, is just 1 times 11, so it's 11 square units, my red region. The area of the circle, which my region is enclosed in, is pi times the radius, which is half of 11 in this case, squared. And so we get 95.03 units squared. So when we're taking the Rioch score, what we're doing is we're taking the area of the region, so my red rectangle's area, divided by the area of the circle. And so when we do that, you get out your calculator, you type everything in, you find that my region here, my red region, has a Rioch score of 0.12. Or simply 12% of the area of the circle is also, happens to be the area of my rectangle. Okay, let's look at a different region. It's a little bit bigger, still a rectangle, a square in this case. And again, finding the area of a square is quite simple. We just take one side. In this case, it's 7.8 units. We square it to get 60.8 units squared. The area of the circle is the same. We haven't changed the circle, so it's still 95.03. When we're looking for the Rioch score now, we'll still take the area of the red square here, but that's 60.8 now, quite a lot larger than the previous one. And then divided by 95.03, and this Rioch score is 0.64. You might just want to think of that as 64%. As a little aside, if your region is exactly the same size as the circle, then the Rioch score will be 1 or 100%. Okay, another test that I want to look at that measures compactness. This is another test we looked at in class. It's called the Polsby-Popper measure. However, we're not going to be using this measure in our analysis. It's just a little bit more complicated than the Rioch score. That one's more simple, so that's the one we're going to come back to. But this is simple enough for us to go over anyway. And it's similar to the Rioch score in that we're comparing areas, again, of regions to circles. So let's get into it. So it might look similar, and it is quite similar. We're just taking one area and dividing by another here, except what we're doing is we're making sure that the perimeter of our region is the same as the perimeter of the circle, or the circumference of the circle. Then comparing their areas. So I have another example for you, so let's look at it. So now I have a star-shaped area, again in a circle here. So my star-shaped, or the perimeter of my star-shaped region here is 3.454 times 10, which gives us 34.54 units. And then the circumference of our circle, which is given by 2 pi r, is 2 times pi times 5.5. This is the same circle, again, that we've been using, which adds up to which multiplies to 34.54 units. So they have the same perimeter. But you can see the star doesn't extend to the edges of the circle. And so in this test, yeah, they normally won't actually touch the outside of the circle. But now that we have confirmed that they have the same perimeter, let's compare their areas. That's the main part of this test. So the circle area, as we know from a previous example, is 95.03 units squared. It's the same area. But then the star area is 25.37 units squared. So that calculation's a little bit involved and would take a couple minutes to go over just on that. So I've omitted those calculations from the slide. You can confirm that on your own if you like. So when we're taking the Polsby-Popper measure, we're taking the area, just like we did before, the area of the star, of the region we're interested in, and dividing it by the area of the circle. So we have 25.37 divided by 95.03. And that gives us a measure of 0.27. Or you can think of that as 27%. Okay, and again, if your region is a circle, then the score will be 1. Okay, so next we're going to get into shortest split line algorithm, and we're going to be using that in a second, along with the Rioch score to analyze a region here. But let's talk about the shortest split line algorithm first. So we have some rules that were given to us from, in this case, Maptitude mapping software in GIS. But I'm not going to read these rules over with you, but what we're going to do is go over an example, just like we've been doing. So here, I've created a region. I've created a state, let's say, and it looks like this. Now, the region on the bottom, in the south, I guess, is red, and that means it's more densely populated than the area green, which is more densely populated than the area in yellow at the top left. So what we want to do first is split this region up in half, not by area, but by population, so that when we split it, half the population will be on one side and the other half will be on the other side. So let's see where I made this split. Okay, so down here in the red is where I made this split. So now we have two halves of my state, the bottom half and the top half. So let's look at the top half for now. So what we're going to do is actually do the same thing with this top region. We're going to split it in half by population. So where did my line go there? Okay, perfect. So with our two halves of the top region, we're going to split each one of those in half again. So let's see what that looks like. There's the first split, and the second split is here. Okay, and it should be noted while I'm going through this that the splits that I'm making are always using the shortest line. So if you don't have that, there are maybe an infinite number of ways you can split a region, but with that restriction, that's really where you're getting the power in the algorithm, is that the line has to be the shortest that it can be. So anyway, I've split up my top half of my state into these 4 regions, and now I'm going to quickly split up the bottom half of my region into 4 regions as well. Okay, here we go. And I just happen to want to split this up into 8 pieces. There may be reasons I would want fewer or more. But now that I have gone through this process, what we can see is in each of my splits, each of my split regions, I should say, it contains the same population, the same number of people. So not the same geographic size, but the same population. Okay. So how does this apply to real life, though? Well, let's take a look at our example of Massachusetts, going back to the 1800s. So this is what the Massachusetts voting regions looks like here. But I want to find a map that's easier to look at. So let's have a look at this one. Yeah, so this one on the left is the same map, or it uses the same data, showing the same thing, but it's a little bit easier for us to use. On the right here, we have from a person named Ivan Ryan at the Center for Range Voting, using US Census data. They've created this algorithm already that takes the population, it takes the shortest lines, and it splits up the state into, in this case, into 9 regions. Okay, and so I think you can see, just by looking, before we really get into our analysis, you can see that the regions, the congressional regions, become simpler, or the shapes become simpler shapes. Okay, I want to show a couple more examples for that to hit home. So let's look at Indiana here. So on the left, we have what the regions actually look like, and on the right, we have the split line districts. Okay, see how simple that is on the right? Final example, we can look at Alabama here, and I don't know why, for example, in number 6 and number 2 and number 1, it looks like almost like an egg, and you've cracked it open, and part of the egg is on one side and part is on the other. I don't understand why that is. But the split line algorithm, as you can see on the right, doesn't consider why that would be. So anyway, we can see on the right we have some simpler districts. Okay, so let's take an analysis here. Let's look at this. So what I want to do is take region number 1 from Massachusetts here. And we're going to look at the split line region first, which is quite similar to the region number 1 in the map on top. So what I've done is I've blown it up. I've cut out the pieces that we don't need using my rudimentary software, and I've done a few calculations. So the diameter of the circle is 212 pixels. I was using pixels for this. So the radius is 106 pixels, which means the circle area is just over 35,000 square pixels. Okay, but now the green region, I have the lengths of the 4 straight lines there, but by cutting it up into triangles and some squares and summing those areas together, I was able to calculate just over 20,000 square pixels for this green region. So if we take the area of our region, 20,000 and some change, divided by the area of the circle, so 35 and some change, we get a REOC score of 0.575. So that was using the split line algorithm. Now let's take a look at the real the real region here. So unfortunately, I don't have great software to have a look at this, and the calculations are a little bit more complex just due to the shape of the region. So here's what I did. I loaded it up. I put 1 in a circle. As you can see on the left, it fits perfectly. Then I took another region number 1, I cut it up into pieces, and I added it to the circle. So here on the right, you can see 2 full region 1s in the circle, and there's still quite a lot of space left over, and I estimate we could put in another full region number 1. Now, it's hard. A lot of the data is retired as I'm trying to go and look for it on the internet and some IP blocks on some government websites for some reason. Wikipedia was able to tell us that the area of this region, the land area, is just over 8,000 kilometers squared. Unfortunately, I don't have a way to relate the real life area and the area of my circle on the screen. And so this is unfortunately, the most sophisticated way I have of analyzing this area. So, okay. If we can fit 2 full regions for sure into this circle, and I suspect we can fit another 3rd region into it, we'll say the REOC score, it must be in between 0.3 and 0.5. Our group's estimate is 0.35. Okay, so I mean, what does that mean? So we have our real life region on the left, and we have a similar region on the right that was done using a split line algorithm here, and there's quite a difference in the REOC score, right? And you can clearly see that the split line was able to make a more compact region. And actually, as we look at all of the regions, even though we didn't really get into it, we didn't calculate them, we can see that the split line makes them simpler, easier to use, easier to look at. Now, you still get some strange regions, like region number 9 here on the bottom, and I mean, sometimes you can't do anything about it. That's literally the land formation. We can't really change that very much. So it's going to look strange, even in a split line system like this. But we can very clearly observe all of the regions are more compact. And yeah, as I mentioned, there are some things that may affect the compactness of a region, like land formations, rivers, mountains, border changes as well can. So let's get into some final thoughts here. We think districting would be more fair if we remove the mind, if we remove the human mind from it. Give the algorithm to the computer, let the computer do it. Okay? It doesn't care about how badly you want to win the vote. Okay? So let the computer do it. The thing is, people will always have the incentive, to want to change the regions, to want to group the 4 or 5 blue dots together that I did before, so that there are 5 red regions and 2 blue regions. Okay, so let a computer do it. It's important also to have a governing body that's going to honor past systems and only update them as large populations require that they be updated. And it's true that you don't always, in every location, get the most fair piece by the split line algorithm. What we are confident in is the overall system will be much more fair if we use that. So with that, we have come to the end of the presentation. So thank you for watching. Thank you for listening. Hope you liked it. I'm not sure if our professor is going to allow comments or not, but if you have any comments, please put them down below. I'll have a look at them and I'll answer them with as good information as I can. So once again, everybody, thank you. And well, see you again maybe in the future.